Parallel axis theorem 1. The equation for the parallel axis theorem looks like this. The moment of inertia about any non-center of mass axis is equal to the moment of inertia about a center of mass axis plus m d squared, where d here is the distance between the center of mass axis and the non-center of mass axis. That's what d is. And m is the total mass. That is the equation for the parallel axis theorem. It's an incredibly useful theorem, and we're going to try and get our minds around it here. This theorem allows us to easily determine the moment of inertia about any non-center of mass axis. Usually, for uniform shapes, the center of mass moment of inertia is found in a table. You can usually look that up. You don't have to do r squared dm all the time. Often you can just look it up in a table, which is awesome. If you want to find out what the moment of inertia about a non-center of mass axis is, then you can usually use that tabulated value, and then you just tack on this md squared portion, and you're done. So let's circle the correct answers here, a little conceptual work. The rotational inertia through any non-com axis will always be larger than the rotational inertia through a center of mass axis. In other words, the rotational inertia, or moment of inertia, those are synonyms. The rotational inertia through a center of mass axis represents a minimum rotational inertia for any object about a given center of mass axis. So let's kick this idea around here by doing this. You can see the picture there. This is a uniform disk that's to be rotated about a point that is not through its center of mass. Clearly its center of mass is in the middle there, and I tried to describe what's happening here. If you stabbed a cardboard pizza disc with a pencil at point P, and pretty soon at point Q, and then held the pencil and whirled the disc around it, that's what we're doing here. Before we start, should the moment of inertia be larger about point P or point Q? And the answer is Q. As the distance from the center of mass gets bigger, the moment of inertia is going to be bigger as well. So let's determine the moment of inertia about point P and then about point Q. Here's what we're going to do. The moment of inertia about the center of mass for a disk is 1/2 m r squared. And you can look that up in a table. So you don't have to derive it every time, or Google it if you need to. That would be part of the right side in the parallel axis theorem. That's this portion right here that I'm pointing at. So that portion is 1/2 m r squared. Now, this other portion, right on the far side here, that's going to depend on how far away our new axis is from the center of mass. So if I can sneak up here, you can see in the picture at the top right corner that point P is a distance of 1/2 r from the center of mass, and point Q is a distance of 3/4 r. Let's determine the md squared portion for each of these. For point P, the md squared portion is equal to the mass of the disk, and then the distance that point P is away is 1/2 r. So then we need to square that, which would be 1/4, won't it? 1/4, and then there'll be an mr squared. Which means that the moment of inertia about point P is going to be 1/4 mr squared, that's what this is, plus 1/2 mr squared. So I think that's going to be 3/4 mr squared. What about for point Q? For point Q, that md squared bit is the mass of the disk, but this time the distance is 3/4 of r, and we have to square that. Now what does that come out to? That's going to come out to 9/16. 9/16 mr squared. 9/16 plus 1/2. Well, 1/2 would be 8/16. So 9/16 plus 8/16, the moment of inertia about Q, I'm getting 17/16 mr squared. And as we predicted in part B up there, which is still on the screen, as the distance from the center of mass increases, the moment of inertia should also increase. 7/16 is definitely bigger than 3/4. I think we look okay.